All right, welcome to today's Explainer. Look, my role right now is basically to serve as your strategic advisor. We're going to take deep learning, which, let's be honest, usually gets thrown around as this complex technical buzzword, and we're going to transform it into your organization's ultimate competitive moat. If you're a non-technical business leader and you're trying to figure out how artificial intelligence actually drives operational efficiency and real-world commercial impact, you are in the exact right place. We're going to look under the hood of these systems, figure out how they actually learn, and map out exactly how you can use them to build just an insurmountable advantage in your specific industry. Let's get into it.
So here's our game plan for today. We're going to start by looking at the paradigm shift, then move through the architecture and raw data, check out the hardware timelines, explore modern generative AI models, and finally wrap things up with commercial impact and governing risks.
Starting right off with Section 1, the paradigm shift. To really wrap our heads around how this technology fundamentally breaks away from the software of the past, we kind of have to understand the limitations of what came before it.
This comparison brilliantly illustrates the core shift we're talking about. We are literally no longer constrained by the massive bottleneck of human-coded rules. Think about it. In the past, traditional software and early AI ran on symbolic logic, right? So if you wanted a computer to recognize a chair, you had to manually engineer thousands of rules. You'd have to tell it, okay, it has 4 legs, a seat, a backrest. I mean, imagine paying an engineer for 3 weeks just to explain to a computer what a stool is. That process, which is called feature engineering, was just incredibly tedious and super brittle. Deep learning completely flips the script on that. Instead of all that manual feature engineering, it uses layered neural networks that automatically extract meaning directly from raw data sets. You just feed the system thousands of raw images, and it figures out the representation of a chair completely on its own. It's an absolute game changer for how software actually operates.
Moving on to Section 2, Architecture and Raw Data. Let's see how this builds into the actual architecture that's making all these automated decisions.
Now I want to highlight the universal approximation theorem. And hey, please don't let the mathematical term intimidate you. To put in plain boardroom terms, this theorem basically proves that deep neural networks can map out essentially any operational problem or complex nonlinear business relationship you throw at them. The only catch? You just need the right data and a network that's deep and wide enough. Whether you're trying to predict consumer demand based on shifting weather patterns or diagnosing a disease from a medical scan, the math absolutely proves that this architecture is capable of finding the pattern.
Looking at this architecture, the absolute most crucial point is how those hidden layers act as automated filters, or extractors. They take that messy, raw input and disentangle it into highly valuable predictive abstractions. Picture the data flowing from the input layer on the left, moving through those hidden layers in the middle, straight to the output layer on the right. Each hidden layer processes the data, untangling those complex abstractions step by step. So the first layer might just find simple edges in an image, the next layer finds shapes, and then maybe the final layer completely identifies a face. This layered architecture is the exact thing replacing all that manual feature engineering, and it's what dramatically boosts predictive performance.
Which brings us to Section 3, Hardware Timelines. And right now, you might actually be asking the ultimate boardroom question. Hey, if the foundational math existed decades ago, why is this revolution happening right now?
Well, as you can see mapped out here, the true catalyst has 100% been the massive evolution of hardware. Back in the 1980s, research actually shifted from symbolic logic over to modern neural networks with the reinvention of backpropagation. But honestly, they just lacked the computing power. In 1990, we saw early optical computing hardware, but the real explosion, the true tipping point, happened in the 2010s. The 2012 ImageNet competition literally triggered the modern deep learning revolution purely because we finally had the hardware to process massive datasets. Breakthroughs in large vocabulary speech recognition followed. We completely shifted from traditional CPUs to highly specialized processors like GPUs and Google's TPUs, tensor processing units, which are engineered specifically to accelerate massive commercial-scale model training. And looking forward, we're even discussing the potential for photonic hardware to enhance energy efficiency in future AI systems. Make no mistake, hardware is the absolute engine of this revolution.
Let's jump into Section 4, Generative AI and Models. Armed with all that immense computing power, we can now use highly specialized network architectures to solve previously impossible problems.
This breakdown perfectly maps out your modern strategic toolbox. It shows you exactly which architectural engine to deploy depending on your specific business need. Convolutional neural networks, or CNNs, are your absolute go-to for visual processing. Think automated medical image analysis. Recurrent networks, like LSTMs, handle sequential data perfectly, which is exactly what you want for speech recognition or complex weather prediction models. Then we have the massive emerging trends, transformers. These are the absolute powerhouses behind today's generative AI boom, directly impacting market competitiveness by creating incredibly human-like text and code. And generative adversarial networks, or GANs, are absolutely brilliant for synthetic creation. They let you generate privacy-compliant synthetic data, meaning you can train robust models without ever exposing actual customer records.
And here we have a brilliant illustration of another specific model called an autoencoder. This is an unsupervised model that learns to compress input data down for dimensionality reduction and then reconstruct it. So why does this matter to you? Because it makes it incredibly powerful for anomaly detection. Imagine training an autoencoder on millions of totally normal financial transactions. When a fraudulent transaction suddenly occurs, the model will struggle to reconstruct it, and it instantly flags it as an anomaly. It's just a prime example of how specific architectures solve problems that were practically impossible for earlier rule-based software.
All right, Section 5, Commercial Impact. Let's translate these technical capabilities directly into actual commercial impact and operational efficiency.
The absolute most crucial point here is the measurable return on investment across every single sector. American Express, for example, is using supervised learning for real-time fraud detection, catching incredibly subtle patterns that static rules miss entirely. In healthcare, deep learning is completely transforming drug discovery timelines by generating molecular structures, literally compressing pharmaceutical research by months. Retailers are leveraging unsupervised learning for automated customer clustering so they can segment audiences without any tedious manual tagging. And over in the supply chain, predictive maintenance models are analyzing IoT sensor data to forecast equipment failures long before they actually happen. The transition from symbolic logic to deep learning has fundamentally changed business capabilities across the board.
Now for Section 6, Governing Risks. Because a truly mature AI strategy requires that we don't just buy this technology, we have to implement robust governance.
With all this great power comes significant operational risk, so you absolutely must architect operational guardrails. First up is overfitting. This is a super common training hurdle where a model basically just memorizes the historical training data rather than actually learning to generalize. You've got to manage this through techniques like data augmentation, adding variety to your data to create much more reliable corporate AI systems. Second, you have to rigorously audit for algorithmic bias. From a purely business standpoint, you do not want your models scaling historical human prejudices. That creates massive brand and compliance liabilities. Third is explainability. Navigating the black box where these networks find correlation but not necessarily causality can be a real headache for regulatory audits. And finally, data ethics. You need strict operational strategies for managing copyright concerns, maintaining data privacy, and navigating ethical compliance during data collection. It's ultimately all about protecting the business.
I want to leave you with this final, incredibly important thought. The algorithms themselves, they're becoming widely accessible. But your proprietary, industry-specific data is your true competitive moat. Deep learning thrives on massive data sets, and your unique data advantages are exactly what enables you to train superior, proprietary models that your competitors simply cannot copy. Deep learning is no longer a research experiment. It is the new operational baseline. So the big question you've got to ask yourself as you leave this briefing today is how will you leverage your proprietary data to build an insurmountable competitive advantage? Thanks for joining today's Explainer.